For a two-component system, we apply the reduced phase equation, which is F is equal to C minus P plus 1. Here the number of component is 2, so we get F is equal to 3 minus P, which is the reduced phase equation. Since minimum number of phases in a system can be 1, hence the degree of freedom for such a system is equal to 2. So we need temperature and composition to define the system if we are defining the system at constant pressure. Let us discuss the system. Point A and point B are the melting point of component A and component B. As increasing quantities of B are added to A, the freezing point of A falls along the curve AC. Likewise, on adding increasing quantities of A to B, the freezing point of B falls along the curve BC. On curve AC, solid A is in equilibrium with the solution of A and B. In the area above ACB, the system exists in the homogeneous solution of components A and B. Along the curve AC, solid A is in equilibrium with the homogeneous solution of A and B, while along curve BC, B is in equilibrium with liquid solution of A and B. Curve BC represents the freezing point curve of component B, and likewise curve AC represents the freezing point curve of component A. Along these curves AC and BC, there are two phases present. So at atmospheric pressure, that is at constant pressure, along the curves where two phases are present, and since it is a two-component system, the degree of freedom is 1. So curve AC and BC are univariant. To define the system at these curves, we need a single degree of freedom. These curves AC and BC intersect at point C. At point C, solid A, solid B and homogeneous solution of A and B is present. At point C, if we apply the reduced phase rule, since there are 3 phases present and the number of component is 2, so we get F is equal to 0, invariant. The system is invariant at point C. C is the lowest temperature at which solid A and B and the liquid solution coexist. Point C is also known as the eutectic point. Area above the curves AC and BC consists of a single phase, that is, 2 components are present as homogeneous liquid solution. So in that region, area above curve AC and BC, applying the reduced phase equation, F is equal to C minus P plus 1. The number of component is 2, number of phases is 1. So the degree of freedom is equal to 2. The system is bivariant. That is, in the region above the curves AC and BC, we need temperature and composition to define the system simultaneously. Now, let me consider a liquid mixture at constant pressure, and if it is cooled from point A and the temperature is allowed to fall until point B is reached on the freezing point curve of component A, that is along AC. At this point, solid A separates out. System consists of 2 phases. So the F is equal to C minus P plus 1. 2 minus P plus 1. The number of phases is also 2. F is equal to 1 along the curve AC. As cooling is continued below B, more and more A separates out and the solution becomes more and more richer in component B. Temperature and composition both changes along the curve BC. An area in the region A, C, D, this area. Solid A is in equilibrium with the solution of a varying composition given by the curve AC, which depends on the temperature. At point D, when eutectic temperature has reached, the second solid also starts separating out. The system at point D has 3 phases. number of phases is equal to 3. So degree of freedom is equal to 2 minus 3 plus 1, that is 0. The system becomes invariant. On further cooling below D, both the solid A and solid B separate out together in a fixed ratio, and the composition of solution remains constant below the line dd dash. Solution phase is completely solidified and the system consists of solid A and solid B. Same is the case at point A dash to B dash. As we cool the system from point A dash to B dash, the system will become more richer and richer in composition in component A, whereas solid B will start solidifying along the curve BC. There is a special case shown by the dotted line when the system is cooled from point A double dash to point B double dash. On cooling from A double dash to B double dash, no solid separates out until point B is reached. At point B double dash, this point, both the solids A and B separate out simultaneously. Temperature and composition remain constant until all the system has solidified.